Next section that we are going to see is a discussion about magnetic charge, whether magnetic charge exists. We know electric charges exist or electric monopoles exist. Similar way, do magnetic monopoles exist or magnetic charges exist? So this question is going to be discussed in this section. In free space, if you consider the Maxwell's equations, if you are considering Maxwell's equations in free space where rho, the charge density is 0 and the current density is 0, okay, you are considering free space. There del dot E is equal to 0. Okay, this one is the Gauss's law. Here the charge density is 0, so we have this del dot E equal to 0. Originally del dot D is rho by epsilon 0, rho 0, so del dot E 0. Then we have this equation del cross E equal to minus dou B by dou T. Okay, the Faraday's law. Now changing that, del dot B equal to 0, then del cross B equal to, we originally had J plus mu 0 J plus epsilon 0 dou E by dou T. Since we are in free space, J is 0, so del cross B is mu 0 epsilon 0 dou E by dou T. So these equations are somewhat symmetric. Why we say symmetric? If you replace electric field by magnetic field here, take the set A, the equation set A. If you replace the electric field by magnetic field, instead of E, if you are using B, and and we replace magnetic field by minus mu 0 epsilon 0 E. Okay, we are replacing magnetic field by minus mu 0 epsilon 0 E. Then this set here you will get del dot B equal to 0, and here you will get del cross B equal to minus dou by dou T. And you are replacing magnetic field by minus mu 0 epsilon 0 E. So this minus will get cancelled and you will get the second set. Okay, you will be getting the second set. Okay, and the reverse is also true. You replace the magnetic field by the electric field. Okay, and this electric field here by the magnetic field. Okay, you are replacing the electric field here by the magnetic field, or rather E equal to, here we replace B by this, so we replace E by what? Minus 1 by mu 0 epsilon 0 B. You will get back this equation. So we can transform or change from one equation set to the other equation set. Okay, so this is somewhat symmetric. We say this is somewhat symmetric. But the rho in Gauss's law, okay, if you are not considering a free space, there will be definitely rho and J. The rho in Gauss's law and J in Ampere's law here, that spoils the symmetry of the Maxwell's equations. Okay, that is spoiling the symmetry of the Maxwell's equations. If you had rho here, this one will have right hand side, yes, rho by epsilon 0, but the right hand side of this equation is 0, so that spoils the symmetry. Also here we have only del cross E equal to minus dou B by dou T, but if you consider the current density also will be here, that will be adding with this mu 0 epsilon 0 dou E by dou T. So the symmetry is lost due to rho in Gauss's law and J in Ampere's law. Now suppose this is an imaginary situation. Suppose we had del dot E equal to rho E by epsilon 0. Okay, rho E is the charge density for electric field. Density of electric charge, rho E is density of the electric charge, and along with this minus dou B by dou T, we had this minus mu 0 Jm. Okay, this is kind of imaginary situation. Jm is the current of or current density of magnetic charge. Then the first equation set becomes del cross E equal to minus mu 0 Jm minus dou B by dou T along with del dot E equal to rho E by epsilon 0. And here see del dot B, originally it is del dot B is equal to 0. Okay, suppose like this, as we found in the as we find in the first equation, the Gauss's law. Suppose we had rho m, a magnetic charge. Rho m is the density of magnetic charge. Then del dot B will be equal to mu 0 rho m, and del cross B mu 0 J. J a subscript is given E. It says it's a current of electric charge, because here we have this current of magnetic charge, mu 0 epsilon 0 dou E by dou T. Okay, so this is symmetric. So the Maxwell's equations in the presence of in a material, in the presence of a charge or current, that will be symmetric. The Maxwell's equations in general, this is a special case in free space. In general, the Maxwell's equations will be symmetric if we had magnetic charge. Okay, if we had magnetic charge, and if we have magnetic charge, there will be magnetic current density Jm. When there is flow of magnetic charge, we will have magnetic current density. So if you have magnetic charge, we will be getting symmetric Maxwell's equations, very symmetric Maxwell's equations for electric field and magnetic field. But unfortunately, God didn't create magnetic charge or magnetic monopoles. So magnetic monopoles do not exist. Magnetic monopoles do not exist. There are no magnetic charges. So the symmetry of the Maxwell's equations is lost. So actually, in Griffith, the author says the Maxwell's equations beg for magnetic charge to exist. Okay, beg for. It badly needs magnetic charge so that the equations are symmetric, because it would fit in so nicely. Okay, it would fit in so nicely. But unfortunately, God has created magnetic charges, so magnetic charges do not exist, and we have the magnetic charge, it's a hypothetical entity obtained following the symmetry of Maxwell's equations. So following the symmetry of the Maxwell's equations, we try to predict the presence of magnetic charge, but experimentally nobody could ever find magnetic charge like electric charge. This shows the continuity equations will be also satisfied very nicely if magnetic charges exist. If you take del dot del cross E, here if you take del dot del cross E, you will get del dot Jm equal to minus dou by dou t of rho m, because del dot del cross B, here you will have del dot B, that is equal to mu 0 rho m, and from that I will get del dot Jm equal to minus dou rho m by dou t, which is the continuity equation for magnetic charges, magnetic charge density. And this is we know the continuity equation for electric charges, electric charge density, del dot G equal to minus rho dou rho E dou t. Okay, but unfortunately, as I said earlier, nobody ever could find nobody could ever find magnetic charge like electric